In this video, an ENACT coach will model 2 strategies teachers can use to support students in taking ownership of computational thinking practices. We'll call these strategies prompting and pointing out. The coach will model how you might prompt students to use computational thinking by making suggestions about how students can use CT practices to approach a problem. Then the coach will model how you could point out when you observe students using a CT practice, whether they realize they were doing so or not. The examples in this video focus on finding the areas of triangles shown on grids, but the ideas could apply anytime students look for similarities and differences in approaches to problems. Let's watch the example of the coach prompting students to use pattern recognition as they complete a table of information about related problems. Students are finding areas of triangles and the areas of the rectangles they drew around those triangles. The purpose of the table they will complete is to help them notice that in each case, the area of the triangle is half the area of the rectangle.
So you should be about finished drawing the smallest rectangle around each one of your triangles. If you need help, compare your work with a partner. Your next step is going to be filling in a table that shows the area of each triangle next to the area of each rectangle. The table will look something like this. But I don't want you to just fill in the table. While you're working, I also want you to do some pattern recognition. So as you're filling in those rows, I want you to think about, what do I notice that's similar across these rows? And if you do notice a pattern, why do you think that pattern makes sense? Why is it happening? If you notice a pattern before you fill out the whole table, you can use the rest of the rows to check if the pattern works for all the triangles in the table. And then maybe you can even talk to a partner when you're done about whether that pattern is going to be true for every triangle and how you know.
After students notice that the area of the triangle is half the area of the rectangle, a next step is to use that pattern to develop a formula for the area of a triangle. Area equals 1/2 base times height. Next, let's watch an example of the coach prompting students to use algorithms as they apply the formula.
It sounds like we've all decided that this is the formula for the area of a triangle. Area is equal to base times height divided by 2. So you're going to get some practice using the formula today, but I want you to think about something. How is using a formula like using an algorithm? Or another way to think about that is, how does a formula tell you the step-by-step instructions to do something? And how can you see the steps? Talk about that with a partner for a minute. So I heard some interesting things. I heard some partnerships say, well, I can tell that the formula tells me to multiply and then to divide. And that's 2 different steps. That's a great point, I agree. So there are some steps in this formula. And then another partnership said, oh, and you know what else? There's these letters in the formula. And each time I use it, different numbers are going to go in there. So every time I use the area formula to find the area of a triangle, I have to decide what numbers I need to put in. And that's just like how we talked about when you use an algorithm. You have to decide how that step applies to your problem. So there's lots of ways that using a formula is like using an algorithm. So maybe as you're using the formula today, you can use what you know about algorithms to help you.
Another video in the ENACT series provides a more detailed example of how you can support students to think through whether the specific steps of an algorithm apply to the problem they are solving. Now, let's look at an example of the coach pointing out how she saw a student using pattern recognition as they found the areas of triangles.
Oh, that's such an interesting idea. Can I try to describe it just to make sure I understand? All right, so you were trying to find the area of triangle A, and as you were looking at it, you thought maybe if I put another copy of A on top there, that would make a rectangle. And you tried that, and it worked. You did get a rectangle. Why was it helpful to have a rectangle instead of a triangle? Oh yeah, okay, that makes sense. So you knew you were trying to find area, and one way to do that is to count the squares. And with a rectangle, you didn't have to worry about those partial squares. It was all whole squares, easier to count. Okay, But then how do we find the area of the triangle after we have the area of the rectangle? Right, okay, yeah, that makes sense. So you just have to divide the area of the rectangle by 2 because you knew 2 of those copies of triangle A made up the rectangle. All right. But then I saw you do something else really interesting. You drew these lines on triangle B and triangle C. How come you did that? Oh, okay, so you noticed something that was similar between A and B, that they both had a square corner. All right, what do we call triangles with square corners? Right triangles, yeah. So A and B were both right triangles. And you thought because of that, you could put a copy of B to make a rectangle as well. And then you also noticed that triangle C had a right angle. It was a right triangle, so you could use the same strategy again. That's a great use of pattern recognition. You notice something similar between the triangles, and you use that to help you understand you could use the same strategy. I wonder if that works for every right triangle.
Encouraging students to describe why they took problem-solving steps can help them solidify their thinking. Let's watch one more example of the coach pointing out how the student developed an algorithm for finding the area of a triangle.
I love that strategy you just described. I think you might have created an algorithm. You want to try writing down the steps? Let's see if we can do it using this triangle as an example. So what's the first thing you did to find the area of your triangle? Okay, so step 1 was divide the triangle into right triangles with a line like that. Okay, and what's step 2? Draw a rectangle around each right triangle. All right, and how about step 3? Find the area of each rectangle. Okay, and how did you find the area? You use the area formula. Okay, so we know the area of a rectangle is equal to length times width. So let's write down our areas for the rectangle on the left. It's 3 by 6, so we have 18 square units. And the one on the right is 6 by 6, so it's 36 square units. All right, how about step 4? Divided the area of each rectangle by 2. Why did you do that part? Yep. Okay, so we're actually trying to find the areas of those right triangles. So to find that, we have to divide the area of the rectangle by 2. Okay, so let's write that into this step just to make it really clear. And we divide by 2 to get 9 square units for the triangle on the left and 18 square units for the triangle on the right. Okay, are we done? No, there's another step? Okay. Add the areas of the right triangle. Right, so we're trying to find the area of the whole triangle, not these 2 separate triangles. So we need to add them to get 9 plus 18, or 27 square units for the whole triangle. Now are we done? Yeah, we got to what we wanted, right? I think you found an algorithm. That's great. Maybe you can use it to find the areas of other triangles too.
As you plan to prompt and point out how students are using CT practices, consider these questions. What are some strategies my students could use to solve the problems in this lesson? How might a CT practice already be a part of or add to those strategies? How might I recognize when I see my students using a CT practice? And how might I identify when it would be helpful to prompt a student to use CT?